All right, hi guys. This is going to be solve problems, practice problems from chapter 4S having to do with reliability. So these don't match up exactly with your problem sets for the week. So I do have some additional problems we're going to run through that aren't in the solve problem section, but by going through the solve problem section on your own or following along, I think it'll really help you understand the reliability practices and how to do these calculations. So we're going to jump right into problem number 2. And this talks about how there's a machine that that needs to be operative. And so they have 2 standby machines just in case the main machine breaks down. The main machine has a 94% chance of working, which is a 94% reliability. And the backups have reliabilities of 90 and 80%. If either of them fail, the backup can be pushed into service. If one fails, the other backup can be used. What's the overall system reliability? So in this problem, we've got a main system with 94%, 90% chance the backup one works, 80% chance the other backup works. What's the overall reliability of the system? So I have this broken down a little bit differently than on your problem set because I'm going to do the chance of failure off to the side here. Whereas on the problem set, I think that you can do these calculations within one cell to figure it out. And I'll show you both ways of doing that. But what we want to look at, just so you see what's going on here, is what's the chance that the main system fails, okay? So the main system is going to fail the inverse of 94%. The inverse means if you have a percentage, 1 minus that percentage is what's left over. The difference between 100% and that percentage is the inverse of it. So 1 minus 94% is 6%, right? 1 minus 94 is 6, okay? So 6% here, that's your chance of failure. Now, by doing it this way, by doing 1 minus that, I actually have it set up where I can copy this down twice, and it'll do 1 minus 90% to leave 10, 1 minus 80% to leave 20. And I want you to view this chance of failure because that's important. Now, you can do this 1 minus a number within a single cell on this reliability, the overall reliability of the system. But I'm going to break it down here so you can see what's going on in each of them. The overall reliability is likelihood of either the main system working or either of the 2 backups. If any of these can work, then the overall reliability of the system is a success, as long as we get at least one of them to work. So we have a main system, that's their base reliability, 94%. We're going to add a little bit to it because we have redundancies. I get to add the chance that backup 1 is needed. So backup 1 is only needed if the first one fails. So 6% of the time, I get an extra 90% chance, okay? So start with 94% and then add to it 6% times 90%. All right. Now what I get to add to it is the chance of needing backup 2. The chance that I need backup 2 is 6% times the 10% times the additional probability. So all of that is going to give me my overall reliability of 99.88%. I can do this same thing by doing individual calculations and then adding them together. So if I was doing this by hand, I could take 94% as my baseline, okay? And I could write that down somewhere off to the side. So that's my starting reliability. Now, what's the chance that I get to use backup number 1? I have 1 minus 94 is 0.06, and I get to multiply that by 0.9, and I get to add 0.054. So 0.054, I'm going to just write that down. That's the additional reliability of having 1 backup. Now, by having a second backup, the chance that I need a second backup is going to be equal to the chance of failure here times the chance of failure here, because they both have to fail in order for me to get to backup 2. And if you watch the other video, that's what I was doing wrong there. I wasn't factoring in that it's this times this times this, and that's where I was getting lost. So chance of first reliability is 1 minus 0.94. So I write down 6% just to have it. Chance of the second reliability is 1 minus 0.9, okay, 0.1. So 0.1 times 0.06 times 0.8 equals 0.0048. So I'd write down 0.0048 So this is the initial reliability, the extra reliability of one backup, the extra reliability of a second backup. Now I can add these three numbers together, and this is going to give me my overall reliability because of the two backups. 0.94 plus 0.054 plus 0.0048. 99.88% reliability. So I said you could do all of this calculation within one cell and not even have this chance of failure, which is how I've got the problem set up. If you want to edit your problem set to resemble this, you're welcome to, as long as you have the overall reliability highlighted in yellow here at the end, and you have all these set up where I can clearly see what's going on with the calculations. You're welcome to edit your templates. So the overall reliability I could have set to equal 94% times 1 minus 94. I can put that in parentheses, so it does the calculation. That gets me 6% just sitting there. Multiply it by 90%, all right? Then I can add to that the chance that I need the other the other second backup. So that's going to be a 1 minus this number, 1 minus 94 times, open parentheses again, 1 minus this number times the chance that the second backup works. And it, oops, what did I do wrong here? I must have missed something here. Times, oh wait, here we go. It's that number plus that. There we go. So what we have is 94%. That's this baseline. I get to add to that a 6% chance that I get to use the 90% chance reliability of backup 2. And then I get to add to that a 6% chance times a 10% chance. Those are the chances that I use backup 2, and the reliability of backup 2 is this one. So really, even though you don't have to have parentheses, to break it down where you can see what's going on easier, I'll bracket this off. You've got initial reliability of 94%. And then in these brackets, you have, the reliability added from this one, which is 0.054. And then at the end, you have all of this done separately. I don't think it'll work with brackets, yeah, but it only recognizes parentheses. But I put the brackets there just so you can see what's going on. This is the initial reliability. This is the added reliability of a first backup. This is the added reliability of the second backup. So you can do all this within one cell. You don't need that chance of failure field there. All right, problem 3 is also a little bit different than our actual problems in that it's a little bit tricky, the setup. It doesn't read quite like you'd expect it to, but what's happened is that you've 3 independent fire alarm systems. Basically, think of this as 3 different smoke detectors on the first floor of the house, right? If there was a fire, what's the chances that a warning would be given? So this doesn't require a backup for one of them. This just requires the likelihood that any one of these systems would fire, okay? And so it is similar to a backup, but whenever you have multiple backups, you get to do something special. So, you've got a backup here, but because they're independent, you get to do, like I said, something special, which is take the likelihood of failure, overall failure, and then take 1 minus the likelihood of failure. You only have a 1 minus this % chance that system 1 fails. So this is the first smoke detector. You've got 1 minus 95%. So 5% chance of failure. And then you've got 97% chance of success. Well, that's a 3% chance of failure. And then here you've got a 99% chance of success. Well, that's going to be a 1% chance of failure. And so if you multiply these together, these chances of failure, what's the odds that all 3 would fail? Well, the opposite of the odds that all 3 will fail are the odds that any one of them would succeed, okay? So if I was to then take 1 minus chance of failure times chance of failure times chance of failure, right? I'm not, you don't need the parentheses the way Excel works, but I'll just put the parentheses on there anyway. 1 minus these 3 chances of failure. So all 3 have to fail. What's the overall reliability? It's pretty darn high. 99.9985% overall reliability. Very high, because any one of them can work and the whole thing works. You can take 1 minus the odds of failure. This is similar to a setup of, let's say I had a coin, 50-50 chance of heads or tails, evenly weighted coin, 50-50 chance of heads or tails. What are the odds that I would flip heads at least once, at least one time out of 4 flips? Okay, so not heads 4 in a row, not, it's not 50-50, right? Because I have to flip them at least once out of 4 tries. Well, I could do all the math individually and then add all those probabilities together. But the thing is, if you look at that problem as what are the possible outcomes? You've got heads or tails, right? Those are the possible outcomes. So if I was to flip it 4 times, 1, 2, 3, 4, the likelihood of me flipping it at least once, you can look at all the possible outcomes here. Heads, 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 heads is one option, right? Heads, 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 tails is one option. Heads, heads, tails, tails is one option. Heads, tails, tails, tails. Lots of possible outcomes, right? And you can keep going throughout this, and then you go, tails, 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 heads, tails, tails, whatever, right? But what matters here is that there's only one probability in which I don't flip heads at least once. There's only one outcome, and that would be for me to flip tails 4 times in a row. Tails, 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 tails. That's the only one out of all the possible outcomes in which I don't flip heads at least once, right? Anyone else, and this list goes on for a little bit longer, but the only one, so ... right? The only one in which I don't flip heads at least once is the total catastrophe failure, right? Tails, 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 tails. So the chances of me flipping tails 4 times in a row, if I can find that number, I don't have to do all the other math of flipping heads at least once on any one of those 4 chances, because the only one in which I don't flip heads at least once is the one where I have 50% times 50% times 50% times 50%. 6.25% of the time, I flip tails 4 times in a row, right? So if I take 1 minus 0.0625, I can save myself a lot of time doing all the math independently on all the chances of me getting heads on any one of those 4. And I can say the chance of me getting heads at least one time out of 4 flips is 93.75% of the time, because I can inverse 1 minus the chance of 4 consecutive tails flips. All right, now let's look at a problem that's set up similarly to your problem this week, in which you have what's called a switch. This is where you have you have 2 systems. If they both have to activate for the overall reliability of the machine to work, and they both have a backup for redundancy, but there's a switch, and that switch doesn't always work. So you can't just take the main system reliability, add the backup reliability, and find the overall system reliability of system 1, because it doesn't always flip over correctly to that redundant system. You have reliability here inside of it. So what you have to do here is take the individual system reliability of 1 is going to be equal to the 95% chance of the main system working times the chance that you need the backup, which is 1 minus 95. So 5% of the time I need the backup. I multiply that by the backup, but then I also have to multiply it by the chance that the switch activates. And what I didn't figure out there is that needs to be inversed. What did I do wrong? This is the inverse of this is correct. So what did I do? I missed one step here. U15. Oh, I multiplied the whole time. All right, what I have here is a 95% chance of the main one working. And then I get to add to that, sorry, I had the multiplication symbol. I get to add to that the chance of the backup system working. So I've got a 95% chance of success already. So it's not going to be lower than 95. I get a little bit extra reliability here. And that is 5% of the time, the times that the main system fails, I get to add to it an additional 95% reliability. So 5% here, 1 minus 95, times 5% chance the backup, 95% chance the backup works, times 95% chance the switch works and allows me to use the backup. So basically everything after here is its own separate section. You don't need the additional parentheses in Excel, but it works. And then here, the same thing happens. So I get 85% chance the system works. I get additional reliability from the redundancy. That additional reliability is equal to the chance I need redundancy, 1 minus 85%, times 85% chance the backup works, times 95% chance the switch works, the 971125. Now that I have each individual system's reliability, the overall reliability is going to be equal to this times this. The 96.64 reliability. Let's do some of that by hand. So let's say I have system one, I've got 95%. We know that that's the reliability. I would just write that down off to the side. Now, what are the chances that I need a backup? I have 1 minus 0.95 is 5% of the time I need a backup, times 0.95 times, which is the backup system reliability, and then 95% chance that the switch works. That gets me additional 0.045125. 0.045 is probably good. Well, let's go all the way out. Okay, and then I can add those two together. Plus 0.95, that gets me 99.5125. All right, good enough. So that's the reliability of system one. I do it the exact same way by a calculator. 85% of my baseline. I get to add to that 1 minus 85 times. So 15% of the time. What's happening here? 1 minus 0.85 is 15%. So 15% of the time I need that backup times 0.85. So that would be the added backup, except the switch isn't 100% reliable. So times 0.95 is 121125. I add that to the initial 85%. Get 971125. All right. So now I can multiply those two numbers together. So 0.995125 times 0.971125. I get a 96.64 rounding up reliability of the system. That's how I do that by hand. And now the overall reliability of 3 systems, if they all have to work, you just multiply them together. It doesn't matter how many systems there are. If there's no reliabilities, you just take this times this times this, whatever those numbers are. Let's say equals this times this times this, 36% chance. So all those are okay reliabilities, but they all have to work. The chance of all of them working is not that good. That's why even if it's, pretty good reliability is 80% or above, that's still a pretty poor overall reliability of the system if they all have to work. So that's a good reason why the redundancies, the backup systems are in place. All right, let's look at the solved problems which require the mean time before failure. This chart from your book, which is on, what page would that be on? It's in 4S. I believe the page number is either 179 or 180 in the physical textbook. If you have an ebook, you just have to navigate to section 4S.2. So this is the chart we're going to be working from here, and let's work on a problem. So this thing says that the weather satellite's expected to work for 10 years. What's the probability of it of not wearing out, meaning lasting at least this many years? Pay very close attention to the way this is worded. the probability of no wear out, meaning it does not fail before, meaning lasts at least this long. So we have operates at least 5, it should be years. So probability will last at least 5 years is going to be equal to the time that we're looking at divided by the mean time between failures. That's going to be equal to this time divided by mean time between failures. I'm going to go ahead and lock that in. And now I can copy this down all the way. So these are the initial values. This is the value we're looking at on our chart. So we need to look at the likelihood of it lasting at least 5 years, 0.50 on this chart. So we looked at this chart, and T divided by MTBF on 0.50 is 6065. I would just write down 0.6065. So you're going to be writing this in. You're not going to be doing a calculation in this cell. The value from chart, you'll type it in. But sometimes it might ask you, what's the likelihood of this failing before? So not lasting at least 5 years, but failing before 5 years. So in this answer field, depending on what it's asking you, you're either going to do equals this number because it's lasts at least. So if the number from the chart is the number, you'll hit equals that number and hit enter. However, if you need to inverse it because it says fails before that time, then your number from this chart needs to be equal to 1 minus that number. So that's how you're going to do that calculation. There's a 60% chance, 60.65% chance it'll last at least 5 years. Pretty good chance considering the mean time is 10 years. But there's a 39% chance it's going to fail before 5 years. So in this case, it's just going to be equal to this because it's asking not failing before that point, okay, on all of these problems. Lasting at least 12 years, 1.2. I look at 1.2 on the chart and I get right here, 1.2 is 0.3012. 0.3012. 2 on that chart, 2.0 is 1353. And 3 on that chart is 0.0498. Not likely that it's going to last that long. So for each of these problems, because it's fail after that point, meaning operate at least that point, meaning not fail before, all those are the same thing, worded differently. You would just copy down the equals formula, copy it down. But again, if it's failed before or not operate that long, you would take 1 minus this number on your answer field here. And then what's the probability that it will fail between 5 and 12 years? So if you look in the book, I think I copied, I did not copy the image. Let me copy this over real quick so you can see the, 1 second. The image that's important here is essentially telling us failing before 12 years would be a certain value, right? Failing before 5 years would be a certain value as well. What we want to take is the chance of it failing in this zone between 5 and 12 years. So we could look at it the other way. We could say failing after 5. If you think of it as all time from 5 years on, okay, from 5 years to any time in the future, and this line is from 12 years to any time in the future, then this zone is the chance of failing between 5 and 12. So we can find this a few ways depending on what we've already solved. And the way that it flows in your actual problem is a little bit different than the way that this practice problem flows, but just pay attention to what it's asking you and what calculations you've done already, and I think you'll be able to figure it out. But just know that if you have this time and you have this time, then that section in between is your probability of it lasting between 2 certain points. So what would that look like in this exact problem? Well, the chance of it failing after 5 years is right here. And, we could just basically copy on the same formula again. And the chance of failing after 12 years is right here. So I just need the difference between those, this minus this. That's that zone, that 30.53%. So 60% chance that it fails 5 years to any time in the future, 30.12% chance of it failing from 12 years to any time in the future. So between 5 and 12 is just the difference of those two. All right, finally, we're going to do a quick thing on availability. This one's actually pretty easy, I think. You just take the time between failures and you divide it by the average time to repair plus the time between failures. So in this case, you've got 25 divided by 25 plus 1, right? So 25 divided by 25 plus 1, you get 26. 25 divided by 26 is 0.9615. That's your availability. That's how much of the time this product would be available. So on calculate or on that was on a calculator. On this, you do this divided by open parentheses, this plus this, close parentheses, done. You can actually just copy and paste this formula and it does it for me, 95.24%, but I can also do it here. I can do 5,000 divided by 5,000 plus 250 is 5,250 divided by 5,250, 0.9524 matches up. All right, so I hope that helps everyone. If you have questions, as always, email me and I'll get back to you. Thanks, everyone. See you in chapter 5.